Hello, here we are in the last part of the 2009 PAT. It's the long question. So in this question, you'll use a simple model to estimate how the energy used by a car depends on its design and how it's driven. Begin by neglecting air and ground resistance. Assume that the car travels at constant velocity between regular, equally spaced stops. Okay, so we're doing some kind of stop-start approach then on all this, where all these are the same and we're moving at this constant velocity. A stationary car of mass m is rapidly accelerated to velocity v, driven for a distance s, rapidly brought to a halt by its brakes. Calculate the energy dispersed by the brakes. Well, that's going to be the kinetic energy of the car, so that's just going to be a half mv squared. So you can see why they're only offering 1 mark for that. Part B, assuming the car restarts immediately, calculate the time between subsequent stops and hence the average power dissipated. Right, so the time between stops is going to be, what have we got? Oh, we're going distance s. So it's going to be s over v, is that's our time between stops. And then what do we want? The average power dissipated. So power equals energy over time, so that's going to be half mv squared multiplied by v over s, so mv cubed over 2s. Nice. C, hence or otherwise calculate the energy used in travelling a total distance d. Right, a total distance d, the energy used, so we want to have power times time. So the time is going to be equal to the distance over the velocity. So we're going to say that the energy is going to be equal to the power multiplied by that. So that is going to be mdv squared, because we're cancelling that v, over 2s. That's good. Taking m is that, v is that, s is that. Calculate the energy used in travelling 1 kilometre. Okay, what would be the effect of doubling the speed to 20 meters per second? Right, so okay, we just got to stick some stuff in it. So we've got, so what was all this? We've got m, we've got v, we've got s. Well, given us everything. I mean, there's nothing here that we haven't got. Right, so that's going to be, energy is going to be equal to 1,000 multiplied by 1,000 multiplied by 100 divided by 200. Right, so we can get rid of that and that and that. So we've got 10 to the 6 divided by 2, which is 5 times 10 to the 5 joules. What would be the effect of doubling the speed? So if we got v times 2, means we got e times 4. So we'd have 20 times 10 to the 5, which is 2 times 10 to the 6 joules. Nice, it's flying along. I'd imagine they're warning at the start we're going to get some, here we go, air resistance. Now consider the effect of air resistance. This can be estimated by assuming that the car has to accelerate all the air it travels through to the same average velocity as itself. You may ignore rapid random motion of individual air molecules in this calculation. Right, so we're treating the air like a solid block. We're ignoring the fact that everything in the air is also moving around with its own individual velocity independent of that frame of reference. So what have we got? Treating the car as a disk with cross-sectional area A travelling at velocity v. Calculate the volume of air swept out in time t. So we've got this disk of A, which is sweeping out some kind of area. So it's moving, velocity times time is distance. So that's v times t. So we're going to have, well, that is it. We just multiply those things together, isn't it? So we've got v times t times A equals the volume of the air. The air's got density d. Calculate the kinetic energy transferred to the air in this time. So the energy is a half mv squared. That's our kinetic energy they've asked for. So that is going to be mass is density times volume. So we need a half times d times v times t times a times v squared. So we've got, let's put them in order, alphabetical order, a d t v cubed. So that's our kinetic energy, hence the power needed. So the power is going to be the kinetic energy divided by the time. So we just need to take the t out. Half a d v cubed. Right, so far so good. Where are we now? F. Taking A is that, V is that, D is that. Calculate the energy used in traveling 1 kilometer. Right, so that's going to be energy is equal to, so we've got a half times A, which is 1, times D, which is 1, times T, which is, so 1 kilometer at 10 meters per second is 100 seconds, multiplied by V, which is 10 cubed, so 1000. So we've got 10 to the 5 divided by 2. So 5 times 10 to the 4 joules. Cool. Using the data above, calculate the, actually on that, I wonder if I was going to calculate the energy used in traveling 1 kilometer. Just wondering if we need to put the energy of the car in, but it's not saying anything about the car. I think the car's already at that energy, at that speed. It hasn't accelerated up. So I think we're just looking at the energy of the air. It's only 2 marks, so I would imagine, yeah, that's probably going to be what it is. In this section, they've said nothing about accelerating the car. So that's going to be the work done against air resistance. So G, using the data above, calculate the distance between stops at which the energy dissipated in the brakes is the same as that lost to air resistance. So we had the energy dissipated in the brakes, which was our half mv squared, and that needs to be equal to, well, what we just worked out here, our half, what was it, a, not m, a d t v cubed. Right, so we got all of that. We can cancel some v's. We can cancel the halves. So we've got m is a d t v. What have we got on this? The m was 1,000, wasn't it? That's what we had for the car. A is 1, D is 1. T, yeah, we had, oh yeah, we got all of these things. T was, what are we doing here? Oh, we've got to calculate the distance between stops. So we don't know what T is because this has changed. So the distance between the stops, okay, is S, which is, so velocity distance over time. So, oh, there we go. Yeah, so V times T is S. Yeah, God, being slow there. So this bit here is S. So that's what we're solving for. So S has got to be equal to 1 kilometer. Yes, yeah, that's right. Yeah, because they've just given us a 1 kilometer here for some distance, but we need to actually work out when these things are the same. Obviously, they're not the same here because we had 5 times 10 to the 5 when we were looking at this before. Now we've got 5 times 10 to the 4. So yes, so we need to change that S value. What have we actually worked out back here on this thing? Oh yeah, that was with S is 100 meters. We had this 5 times 10 to the 5. So yeah, we're changing these things around to get the the energies being the same as each other. If it's happening every 1 kilometer, then we've got we're getting less dissipation because we're not braking as often. We're braking 10 times less. So that energy that we had before, the 5 times 10 to the 5, that was for braking 10 times in a kilometer. If we brake once in a kilometer, it's going to drop it by a magnitude of 10, a factor of 10, I should say, which has now made it the same as the 5 times the 10 to the 4 that we worked out there. Yes, that all makes sense, right? I'm happy now that we've done the right thing on that. So S is 1 kilometer. So comment on the significance of these calculations for the design of cars optimized for driving in cities and cars optimized for driving on highways. Highways, this is a English university. Motorways. Anyway, so we got cities or these highways. So if we're in cities, then we're going to have, that's going to be a small s. We're going to be stopping and starting more often. So we got a small s, which means that our, well, as we've just seen, the effect of the brakes will dominate. So braking will dominate. Braking dominates, which means we need to, so it's our half mv squared that is dominating. So we need to be moving at, well, we want to have light cars. So we want to have, yeah, lighter cars. So we got a low m, and we want them to be efficient at low velocity. At low velocity, so we can move around at low velocity. Also, it might be something you can do with the brakes as well, to do something with that energy when you're decelerating. Decelerate into a charger in an electric vehicle or something. And then we've got, for the reluctantly called highways, so we're going to have a large S. So we're going to have the air resistance dominates. Air resistance dominates. Because as we saw, the larger we're getting on S, the less frequently we're braking. So, and every time we brake is when we get a load of half mv squared. You only get that when you brake. So if you're braking less, the air resistance is going to be dominating. So that means we're going to be, we want to prioritize aerodynamics and having a, well, we can't really change the density of the air very well, but we can change the cross-sectional area. We can change A. So we want to have a low A, low cross-sectional area. Yeah, it's a nice question, that one. It was very coherent in the way it was put together. There were a few things to keep an eye on, and I think that unpicking of G certainly helped with exactly what was going on as S was changing. Those getting a load of kinetic energy every time we brake, so that's why we're getting that factor of 10. So it's quite a nice question, really. There was nothing massively complicated, but it needed an overall coherent view of the question that wasn't trivial. So I quite like that one. So that concludes 2009, Pat. So onwards to 2010.